Hello, and welcome to Zeta Math. In the last video, we told the story of how real-valued functions from calculus naturally give rise to functions with complex inputs and outputs via a process known as analytic continuation. In this way, our series definition of the zeta function, which is initially defined only for the real numbers greater than 1, gives rise to a function uniquely defined at every complex number except s equals 1. When we talk about real functions, we visualize them using a graph like this. For example, the fact that zeta of 2 is pi squared over 6 is represented in this graph by this point. When we instead want to visualize the full range of complex inputs and outputs of a complex function, I'll split off the input and the output into separate planes like this. In this image, the fact that zeta of 2 is pi squared over 6 looks like this. But now, we can show the values of the zeta function at any complex number by moving this dot in the input plane and tracking its value over here in the output plane. The graph of the zeta function on the real line actually looks quite simple. In fact, not all that much different from the graph of something like 1 over x minus 1. But from the viewpoint of the complex numbers, we can see that if we run our input point over around here, the output behaves in a quite complicated way. From the point of view of this picture, the Riemann hypothesis is all about the points in the input space where the output takes the value 0. The zeta function is 0 at each negative even integer. So if I wobble this point through the input space, you can see that every time it passes through one of the negative even integers, the output at that point is precisely 0. These zeros of the zeta function are called the trivial zeros. It is known that all of the other zeros lie somewhere in this zone, between real part 0 and real part 1, known as the critical strip. It is also known that the zeros within this strip are symmetric across this center line. So for example, if there was a 0 here, we would automatically know that there was a 0 here. The Riemann hypothesis is the claim that in fact all non-trivial zeros of the zeta function lay exactly on this axis of symmetry. In today's video, we're going to talk about integrating complex functions. This will allow us to approximate the coordinates of the non-trivial zeros of the zeta function. As we talked about in the previous video, the way we extend the zeta function and other real functions to the complex numbers hinges on the observation that our usual Taylor series from calculus can be evaluated at complex numbers as easily as they can be evaluated at real numbers. For example, if we want to know what e to the I should be, we take this Taylor series for e to the x, and we plug in I and look at the partial sums. From this table, those partial sums seem to converge to a number that's approximately 0.54 plus 0.84i. Let's rewind here and take a closer look at the series we got for e to the I. Simplifying just a little bit, we get 1 plus I minus 1 over 2 factorial minus I over 3 factorial plus 1 over 4 factorial plus I over 5 factorial, and so on. Now let's pull apart the real and complex parts of this series. The real part is 1 minus 1 over 2 factorial plus 1 over 4 factorial minus 1 over 6 factorial, and the complex part is 1 minus 1 over 3 factorial plus 1 over 5 factorial minus 1 over 7 factorial, and so on. These look suspiciously familiar. Let's bring back that list of Taylor series from before. the real part here is exactly cosine of 1, and the complex part is exactly sine of 1. So very strangely, it's true to say that e to the I is exactly cosine of 1 plus I times sine of 1. Of course, sine of 1 and cosine of 1 aren't particularly nice numbers. But by modifying our starting point over here, we can actually replace those 1s with any number we want. If instead of sine of 1 and cosine of 1, I would prefer to have, say, cosine of theta and sine of theta, then I should start with evaluating e to the I theta instead of just evaluating e to the I. Churning through almost exactly the same algebra and pulling apart the real and complex parts again, we find that in fact e to the I theta is equal to cosine of theta plus I sine of theta for any real number theta. This relationship is known as Eulers identity. This identity has many consequences that look pretty absurd at first glance. For example, if I just choose theta to be 2 pi, then this identity tells me that e to the 2 pi I is exactly equal to 1. This actually connects to one of the mysteries from the previous video. Here's what we were doing last time. We started with the real function natural log of x, and then we used the Taylor series at x equals 1 to extend the definition of natural log into the complex numbers. And then we extended it again, continuing to extend it along this path until we got back here to 1. Somewhat confusingly, we no longer found that natural log of 1 was 0. But rather, the analytic continuation was telling us that the natural log of 1 was 2 pi I. Nothing I can say will make this not weird. But if you recall what it is the natural log function is supposed to be doing, it's supposed to be identifying what power of e a number is. So when we take the natural log of 1, we're really asking, what power of e should we take in order to get 1? Of course, our default answer should be the 0th power, because e to the 0th is 1. But in light of what we've just learned, it's also true that e to the 2 pi ith power is 1. The same is true of e to the 4 pi ith power, and the 6 pi ith power, and so on. Indeed, totally unexpectedly, just like the functions sine and cosine, the function e to the z is periodic. Except rather than having period 2 pi, like sine and cosine, e to the z has a period of 2 pi I. What does this mean exactly? Well, if you look back at the graph of sine, you see it has the pattern of this repeating wave. If we want to express that algebraically, then we would write that sine of theta plus 2 pi is equal to the sine of theta. In the case of e to the z, because we're thinking of this as a complex function, that's harder to visualize, but algebraically we can write it almost the same way as the statement that for all complex numbers z, e to the z plus 2 pi I is equal to e to the z. We can think of this as breaking the complex plane into these 2 pi I height strips, where the values of the function are identical at the corresponding points in each strip. What this means is that whenever we take the log of a complex number, we get not one answer, which is what we're used to, but rather we get infinitely many answers. All of those answers will differ from each other by a multiple of 2 pi I. Again, in a somewhat weird way, analytic continuation has figured out what the function natural log is trying to do, and then fixed it for us by identifying that 0 was not the only log of 1. This weird ambiguity will actually prove to be very useful when we're identifying the zeros of the zeta function later. Last time, we talked not just about extending the values of a function to the complex plane, but also the values of its derivatives. It turned out that once we understood how to use Taylor series to extend functions from being defined on the real line to being defined on the complex plane, the notion of the derivative of these functions was essentially free. Our main goal today is to talk about the other half of calculus, integration. Remember that there are two flavors of integral. There's the definite flavor, which in single variable calculus corresponded to something about areas, and indefinite integrals, which corresponded to antiderivatives. Let's start with the indefinite flavor. An indefinite integral is by definition an antiderivative. That is, if we ask for the indefinite integral of tangent of x dx, the answer is minus the log of the cosine of x, because the derivative of minus the log of cosine of x is tangent of x. We usually put this little plus c here on the end of the answer to remind us that the derivative of minus log of the cosine of x plus 7, or any other constant we choose to put here, will also be tangent of x. Let's think about what it looks like to try and do this with tangent of z instead. Remember that for points near 0, we evaluate tangent of z by using the Taylor series for tangent of x centered at x equals 0, which is given by x plus x cubed over 3 plus 2x to the 5th over 15 plus 17x to the 7th over 315, and so on. That is to say, for z near 0, tangent of z equals this. If we want an antiderivative of tangent of z, one way to obtain that is to use the power rule to integrate this series term by term. The result of that is c plus z squared over 2 plus z to the 4th over 12 plus z to the 6th over 45 plus 17z to the 8th over 2520, and so on. We can verify that this is exactly the Taylor series for minus log of cosine of x centered at x equals 0, with all of the x's replaced with z's, as you might expect. But since everything we do with complex functions is happening in terms of power series, we actually get away without having to use any derivative or integral rules at all, except for the power rules, as we did in this example. To understand what happens with definite integrals, let's start with this familiar-looking one, the integral from 1 to 2 of 1 over x dx, which represents the area under the graph of y equals 1 over x between 1 and 2. At first, we might expect that we can make sense of this if we complexify it by changing the x's to z's and replacing the limits with complex numbers, like, say, 1 and I. While it makes sense to refer to the real numbers between 1 and 2, it does not make sense to refer to the complex numbers between 1 and I. This inability to talk about betweenness of complex numbers is a large part of what distinguishes them from real numbers. The key to making sense of this is a concept we introduced in the previous video: paths. Instead of just specifying the start and end points of 1 and I, we also need to specify how we get from 1 to I. Here are several different paths from 1 to I that we could choose. I'll go ahead and label each path with the value of the integral of 1 over z dz over this path, just to show you that once we've made sense of the idea of this integral, it will in fact depend on which path we choose. Before we take this further, I want to point out that this is not a totally new phenomenon for us. Indeed, the integral from real calculus is not just dependent on the endpoints, but also on the path between them. It just so happens that in the real line, there's really only two paths that we could choose, the left to right path and the right to left path. And the values of those two integrals are different by exactly a minus sign. Let's talk now about how we translate from a path and a function to a value for the integral. In single variable calculus, we do this with something called Riemann sums. In this particular example, we break up this interval from 1 to 2 into a bunch of pieces, starting at x0 equals 1, then up to x1, up to x2, and so on up to xn equals 2. Within each segment, we'll choose a point that we'll call xi star, and we'll use that point to define a rectangle. The base of that rectangle will be this segment between xi and xi plus 1, and the height of that rectangle will be the value of the function at xi star. Our Riemann sum is then the value we get when we take the total area of all of these rectangles put together. In order to obtain the value of the integral, we have to take a fancy sort of limit as we shrink the length of each of these segments to 0. Let's rewind back to when there were n rectangles, and let's try and write out a formula for what the total area of those rectangles is. The area of the ith rectangle is going to be the length of the ith segment times the value of the function at xi star. That is, it's going to be f of xi star times x sub I plus 1 minus x sub I. To get the total area of all of the rectangles, we need to take a sum as I goes from 0 to n minus 1 of this quantity. When we want to switch over to a complex function, we're going to do the same thing with the curve that connects the starting point and the ending point. Namely, we're going to break it up into segments. Again, I'll label the starting point here z0, the next point z1, and so on up to the last point I'll call zn. Between each pair of points, zi and zi plus 1 on the curve, I'm going to choose a point that I'm going to call zi star between them. Then, we'll go ahead and just calculate this sum as I goes from 0 to n minus 1 of f of zi star times zi plus 1 minus zi. The integral across the curve of f of z dz is then the limit across all of these sums as we shrink the length of the individual intervals towards 0. The biggest distinction to be aware of here is that this zi plus 1 minus zi term no longer has anything to do with the width of a rectangle, but rather this is some strictly complex number indicating the direction the curve C is going. Here, I want to visualize this happening for the integral of 1 over z along this quarter circle, traveling from a start point of 1 to an endpoint of I. I'm going to break this quarter circle into 3 segments and label the start and end point of each segment. Let's focus our attention on what happens in the second segment here, which starts at root 3 over 2 plus 1/2 I, and ends at 1/2 plus root 3 over 2 I. I'm going to choose the point root 2 over 2 plus root 2 over 2 I on this segment to be my z1 star. Thus, this interval contributes 1 over root 2 over 2 plus root 2 over 2 I times 1/2 plus root 3 over 2 I minus the quantity root 3 over 2 plus 1/2 I. If we approximate the value of this expression, we find that it is about 0.517 I. Working out the contribution of the other two segments gives us the approximation that our integral is about 1.55i. If we gradually increase the number of intervals, we can watch as this estimate for our integral seems to converge to about 1.57i, which is very near to its exact value of pi over 2i. If we repeat the same process, but instead take this 3/4 circle the other direction to get from 1 to I, then we see the results seem to be converging to minus 3 pi over 2i instead. Again, I want to repeat, the path we choose between the endpoints very much matters in the value of the eventual integral. As a second example, let's look at the function g of z equals z squared. And let's examine the values we get as we integrate it along various paths from 0 to 3. To start, we should note that if we take the path that goes directly from 0 to 3, then the procedure we have just described gives us exactly the usual integral from 0 to 3 of z squared dz, which we know how to evaluate normally. Take the antiderivative of z squared, which is z cubed over 3, plug in the endpoints, 3 and 0, and subtract, giving us that the value of the integral of z squared along this path is 9. Of course, there are lots of paths from 0 to 3, and so we can try some more exotic ones. I'm going to draw in a bunch of different paths from 0 to 3, and as I do, I'm going to show you the value of the integral along each path, so that you can see how it changes as I change the path. Or in this case, how it doesn't change. No matter how weird I get with this path, we keep getting exactly the same value. And this is totally unlike what happened with the function f of z equals 1 over z just a moment ago. For the function z squared, even though when I change the path, I change every little piece of the integral I'm calculating, all of those changes exactly cancel out, leaving the final value of the integral unchanged. This property is called path independence. No matter what path I take from 0 to 3, the integral along that path of z squared will always be 9. And that's actually true no matter what 2 points I pick. If I choose some point z0 and some point z1, the integral will be the same regardless of what path from z0 to z1 I choose. So in the 1 over z example, the integrals we get are very much path dependent. That is, different paths sometimes lead to different integrals. But in the case of z squared, the path is essentially irrelevant. So why? What's going on? The first culprit that we might be inclined to look at here is the singularity of 1 over z here at z equals 0. Is this the problem? In a way, yes, but it's more nuanced than that. To see what I mean, let's have a look here at a third function, 1 over z squared. This function also has a singularity at z equals 0. Does that mean that this function will be path dependent, like 1 over z? Let's find out. Here, let's pick 2 points, say -1 and 1. And let's look at a number of paths from -1 to 1 and see what the value of the integral is. And as you look at all of these different options, you'll see the value of this integral never changes. So, just like z squared, it turns out that integrals of the function 1 over z squared are also path independent. Note, I can never have my path pass through the point 0, because the function is undefined there, but I can certainly dance around it in all of these various ways. So why is this? The answer has to do with the fundamental theorem of calculus. But not the fundamental theorem of calculus for real functions, but rather the analogous one for complex functions. Let's recall that the real fundamental theorem of calculus says that if you want to evaluate the integral from a to b of little f of x dx, and we happen to have a function big F of x laying around with the property that the derivative of big F of x is little f of x, then the integral from a to b of f of x dx is just big F of b minus big F of a. Here we can see a really bizarre property of the fundamental theorem of calculus. The answer to the integral depends only on the information at the endpoints. Nowhere on this side of the formula does anything between a and b play any role. To what extent does this hold for complex functions? Let's flash back to an example I showed on the screen earlier, where here we're integrating the function z squared from 0 to 1 plus I along these paths, and we got that the value of the integral along each of these paths was minus 2/3 plus 2/3 I. If we take the antiderivative z cubed over 3 of z squared and blindly apply the fundamental theorem of calculus, what we would get was that the value of this integral should be 1 plus I cubed over 3 minus 0 cubed over 3. And indeed, this simplifies exactly to our answer. Indeed, it's actually the case that the real fundamental theorem of calculus carries over to the complex function z squared with no modifications. That is to say, if c is a curve from z0 to z1 in the complex plane, then the integral of z squared dz over the curve c is exactly z1 cubed over 3 minus z0 cubed over 3. Likewise, for the function 1 over z squared, we have the antiderivative minus 1 over z, and then it is true to say that as long as z0 and z1 aren't 0, and c is a curve from z0 to z1 that does not pass through 0, then the integral of 1 over z squared dz along the curve c will be exactly minus 1 over z1 minus 1 over z0. So what goes wrong with 1 over z? How is it that integrals of 1 over z end up being path dependent? Let's pull up our example of integrating 1 over z from 1 to I along this quarter of the unit circle. Why can't we just take an antiderivative of 1 over z, plug in the 1 in the I, and be done with it? The problem is that the antiderivative of 1 over z is the natural log of z, which, as we saw last video, is not actually a function at all, but something intrinsically multi-valued. That is to say, log of 1 is 0, but it's also plus 2 pi I, minus 2 pi I, plus 4 pi I, minus 4 pi I, and so on. Likewise, the log of I is pi I over 2, but also 5 pi I over 2, minus 3 pi I over 2, and so on. So when we try to apply the fundamental theorem of calculus by plugging in 1 and I to natural log, we have this sort of slot machine effect where I can spin these dials to whichever value of log of I and log of 1 I want, giving a bunch of different answers for the value of this integral. But of course, this specific integral doesn't have a whole bunch of values. It only has one value. In this case, that value is supposed to be pi I over 2, which corresponds to taking the value pi I over 2 here and the value 0 here. If instead we took our 3/4 circle path going the other direction, that ends up giving us a value of minus 3 pi I over 2 instead. No matter what weird path I take, it will correspond to some choice of a position on these two wheels, which will give us one of the many possible values of an integral of 1 over z from 1 to I. If we want to be precise about which value it is we're supposed to take for log at each of these points, what we do is we choose 1 at the starting point, and then we analytically continue log along our path to evaluate it at the ending point, as we talked about in our previous video. So let's try and give a clear statement of what the fundamental theorem of calculus says in general for complex functions. If the single-valued function capital F of z is an antiderivative of lowercase f of z, and both are defined around the curve C with start and end points z0 and z1, then the integral of f of z dz along the curve C is equal to big F of z1 minus big F of z0. What fails for 1 over z along these various curves that we've laid out is that it's impossible to choose a single-valued function, which is an antiderivative of 1 over z along both of these paths simultaneously. Remember that the antiderivative of 1 over z is log of z, and log of z is not single-valued as a complex function. A different viewpoint towards what's going to end up being the same phenomenon we've been observing is to ask the question, what happens if we integrate a complex function around a loop? This is important enough that often you will see integrals around a loop with an additional O here on the integral sign. This O doesn't actually change the meaning of the integral at all, and if I dropped it, it would not change the value of the integral. It's only there to emphasize that the integral being calculated is around a closed curve. So let's pick a random loop like this one, and ask what happens if we integrate the function z squared around it. I'll pick 2 different points on this loop, say z0 and z1. And then I can view this loop as consisting, really, of 2 different paths from z0 to z1. I'll call these paths c0 and c1. Because of the fundamental theorem of calculus, we know that the integral of z squared dz along c0 and the integral of z squared dz along c1 are both equal to z1 cubed over 3 minus z0 cubed over 3. So then what's the integral around this loop? Well, the integral around the loop has 2 pieces. The first piece is the integral of z squared dz along c0. The second piece is actually minus the integral of z squared dz along c1. The minus sign is here because we're actually traversing the curve c1 backwards. That is to say, we're starting at z1 and going to z0 instead of the other way around. But, since these 2 values are equal, this is just saying that the integral around the loop is 0. A different way to think of this is to think of a closed curve as really being a curve that goes from a point z0 on the curve to itself. So that when we then apply the fundamental theorem of calculus, we end up getting z0 cubed over 3 minus z0 cubed over 3, which is, of course, 0. Regardless of how you see it, the punchline here is that if you integrate the function z squared dz around a closed curve, the answer will always be 0. Try to convince yourself the same thing works for the function 1 over z squared, as long as the curve does not pass through the point z equals 0. Notably, this does not work for 1 over z. If we integrate 1 over z around the unit circle, then by putting together our 2 previous calculations, we get pi I over 2 for this piece of the loop, minus a minus 3 pi I over 2 for this part of the loop, which is 2 pi I. The fact that the integral around this loop is not equal to 0 can be thought of as alerting us to the fact that something weird is going on inside this loop. In this case, The weird thing is the singularity at z equals 0. So what happens if we choose to integrate 1 over z around this loop instead? Well, as it happens, we get 0. And here's why. What we want to do is we want to take the Taylor series for 1 over z, centered at this point, z0. Then we're going to write that as the sum of an times z minus z0 to the n. And notably here, I don't actually have to calculate what any of these numbers are, because that's not actually going to be relevant in the argument I'm going to be making. Now, what we know from the previous video is that this Taylor series converges inside of this circle. Just to remind you, the Taylor series of a complex function will always converge within a disk whose radius is equal to the distance from its center to the nearest singularity, which in this case is at z equals 0. Within this disk, we can write down an antiderivative of 1 over z just by integrating the power series term by term, giving us capital F of z equals the sum of an times z minus z0 to the n plus 1 divided by n plus 1. But now we have an antiderivative of 1 over z that is a single-valued function defined on the whole loop. So the fundamental theorem of calculus applies. And then by our exact argument from earlier, this integral must be 0. With more care, you can show that actually the integral of 1 over z around any closed loop that does not contain z equals 0 is 0. Next question. What's the integral of 1 over z around this square? With what we've done so far, we can actually argue that this integral must be exactly 2 pi I. Why? Well, let's start with the unit circle, where we know the integral is 2 pi I. And now let's figure out what happens if we try and replace this quarter of the unit circle with these lines instead. How much has this changed the answer to our integral? Well, we've subtracted the integral along this quarter circle and added the integral along this line and the integral along this line. But these three together are exactly the integral along this closed loop. But that closed curve doesn't contain the point 0, and so this integral will be 0. So the integral along this 3/4 circle 1/4 square is also 2 pi I. But of course we can apply the same argument to this corner, and this corner, and this corner, and then we learn that the integral around the square is exactly 2 pi I. Indeed, you can likely convince yourself that we could change the unit circle into any sort of curve going counterclockwise around z equals 0, and the integral along any one of those curves would be exactly 2 pi I. To be slightly more precise in stating this, I want to make a distinction between closed curves, which are just curves that start and end at the same point, and simple closed curves, which have the additional requirement that they never intersect themselves. For the purposes of defining and talking about the integrals we've been doing, whether the curve intersects itself or not is irrelevant. But for what I'm about to say, we need to be careful that we're talking specifically about simple closed curves. Summarizing what we've learned, we get this. If C is a simple closed curve traversed counterclockwise, then the integral of 1 over z dz along C is either 0 or 2 pi I, and it's 2 pi I precisely when the curve contains z equals 0, and it is 0 otherwise. Exactly the same methods we use to prove this show that if f of z is any complex function, and C is any simple closed loop, if C contains no singularities of f of z, then the integral of f of z dz along C will be exactly 0. Or, put a different way, if we ever find a simple closed curve C where the integral of f of z dz around C is not 0, then the curve C definitely contains at least one singularity of f of z. What does all of this mean for the zeta function? Well, recall the zeta function has only one singularity, and that singularity is here at s equals 1. Thus, if we integrate zeta of s around any loop, then the integral will be 0, unless that loop happens to enclose the point s equals 1. By some coincidence, it happens that whenever the loop does enclose the point s equals 1, the integral will take the value exactly 2 pi I, just like the function 1 over z we studied earlier. So why does all of this matter? One reason is that in general, it's very difficult to identify zeros of complex functions. To see why, I first want to think about how we would identify zeros of real functions. So let's take the function f of x equals x to the fifth plus x minus 1. In this graph, we can plainly see that there is a zero of this function here at this point. And that is backed up by something called the intermediate value theorem, which basically says if it looks like a graph of a continuous function crosses the x-axis, then it really does, and thus we have a zero here. To put that a bit more precisely, I can calculate that f of 0.7 is negative, and f of 0.8 is positive. And the only way for this graph to get from a negative number to a positive number is by crossing the x-axis in between. But there's that word between again. And remember, the word between doesn't play nicely with complex numbers. How will I ever know if a complex function takes the value 0 at all? The key again is to think in terms of closed loops. If I stick to this polynomial f of z equals z to the fifth plus z minus 1, then I can draw a circle here in the input plane, and look at where all of those points end up in the output plane. The points inside this circle in the input plane map exactly to the points inside this loop in the output plane. In this particular instance, you can see that the image of this circle in the output plane does not enclose 0. And so it is not possible that any point on the inside of the circle maps to 0. That means that there were no zeros of our function inside this circle in the input plane. With this method, it's fairly easy to see that this circle definitely does enclose a 0 of this function somewhere. Unfortunately, even for relatively simple functions, the images of circles can get quite complicated. How will we decide if this complicated curve actually encloses 0? And perhaps more importantly, how will a computer decide if it encloses 0? The key here is to use complex line integrals, like we've learned about today. At first, we might want to take the integral of z to the fifth plus z minus 1 dz along C. But this won't actually help. Why? Well, because z to the fifth plus z minus 1 doesn't have any singularities anywhere in the plane, so it definitely doesn't have any singularities inside this circle, and hence, this integral will be 0 no matter what circle C we choose. The secret is to make the zeros of z to the fifth plus z minus 1 into singularities. And fortunately, there is a very easy way to do that, which is to replace z to the fifth plus z minus 1 with 1 over z to the fifth plus z minus 1. Anywhere z to the fifth plus z minus 1 is 0, this becomes 1 over 0, which means that there's actually a singularity of this function. Now, I can move this circle around and track the value of the integral of 1 over z to the fifth plus z minus 1 dz across the circle, and you can watch how it turns non-zero exactly when our loop encloses one of these 5 points, and stays 0 otherwise. By strategically changing the shape of our loop, we can obtain the coordinates of these 5 zeros to whatever precision we'd like. For the zeta function, we can do the same thing. And here we're actually helped by the knowledge that all of the non-trivial zeros of the zeta function are confined to this strip. What we do then is to start with a rectangle here and calculate the integral around this rectangle of 1 over zeta of s ds. Then I allow this rectangle to drift up the critical strip, and whenever this integral is not 0, it means that we've identified a 0 of the zeta function. The first such 0 we find is here with imaginary part between 14 and 15. The next has imaginary part between 21 and 22. And the next has imaginary part between 25 and 26. Our method works, but it has 3 key problems. The first problem is that we're calculating this integral by approximating it, meaning that we're getting a number that is not the exact value, but that is close to the exact value. But then we're asking the question, is this number 0 or not? And that is quite a challenging problem computationally. If you've ever heard the adage, don't compare floating point numbers for equality, that's exactly what we're trying to do here. The second, and actually the most minor of our problems, is that we're actually making a converse error here. The true statement is that if zeta of s has no zeros inside the rectangle C, then the integral around C of 1 over zeta of s ds is 0. That does give us what's called the contrapositive implication, which is that if the integral around the rectangle of 1 over zeta of s ds is not 0, then zeta of s has zeros inside our rectangle. But we also want to know that if the integral around C of 1 over zeta of s ds is 0, then it means that there are no zeros inside the rectangle. And unfortunately, that implication is in general false. To see why, let's imagine that we were trying to find the zeros of the much simpler function z squared using this method. To do this, we would look at the function 1 over z squared, and then we would move this closed curve C around the plane and look for when it happened that this integral was not 0. So for example, if we looked at this closed curve over here, the integral would be 0. Good, there are no zeros inside that curve, that's what we expect. But unfortunately, the integral of 1 over z squared dz around this curve is also 0, even though this curve definitely encloses the point z equals 0, which is a 0 of z squared. So why is it we failed to find this 0? Well, it's because, as we saw earlier, 1 over z squared has an antiderivative, namely minus 1 over z, which is actually defined everywhere except for z equals 0. Thus, in particular, it's defined on every circle that contains z equals 0. And hence, every integral of this function around one of those circles is exactly 0. I actually find this quite unintuitive, because it's basically saying that because z squared actually has a double 0 at 0 rather than only a single 0, we've actually made that 0 harder to find. We'll elaborate on this in the next video. The conclusion here is that we can use the method outlined in this video to find zeros of the zeta function, but we're not guaranteed that this method will find all the zeros of the zeta function. It might miss some well-camouflaged zeros, like the 0 z equals 0 of z squared. The third problem is probably the biggest, And that problem is connected with why we were trying to nail down where the zeros of the zeta function were in the first place. Namely, we were attempting to verify the Riemann hypothesis, which says that the real part of all of the non-trivial zeros of the zeta function is exactly 1/2. Unfortunately, no amount of approximating a complex number is going to allow us to prove that the real part of that complex number is exactly equal to 1/2, and not just a number that's very close to 1/2. Thus, while our method does allow us to find many zeros of the zeta function, it doesn't actually allow us to verify the Riemann hypothesis for any of them. Fortunately, all of these problems are fixable if we dig a little bit deeper into what a singularity of a complex function is and what it looks like. We're going to do this next time, when we're going to talk about a specific kind of singularity called a pole. We're going to talk about a generalization of a Taylor series called a Laurent series. We're going to put this all together with something called Cauchy's residue theorem. And with all of these tools together, we're going to be able to actually prove that the Riemann hypothesis is true, at least for these first few zeros of the zeta function. Thank you very much for watching. If you enjoyed this video and would like to support the production of our content, you can leave a tip by clicking the thanks button below this video. Everyone who contributes will be thanked in our next video. If you'd like to get in touch with us, please email zetamathvideos@gmail.com. If you're interested in Sudoku or other puzzle-related content, check out our second channel, Zeta Math Does Puzzles. We stream there twice a week, so come join in the fun, or just stop by and say hi. Thanks again for watching, and we'll see you in the next Zeta Math video.